Hello friends. In today's class we are going to solve question related with multi-level page table. Welcome here, and we are talking about this question related with this multi-level page table. A processor has 36-bit physical addresses. Okay, so 36-bit physical address. And this is the 36-bit physical address. And 4 kilobyte page size. So 4 kilobyte means of this 4 kilobyte. Okay, 4 kilobyte page size, and here in that way this will become 12 bits byte addressable, and this will become 20 bits. Okay, a 3-level page table is used for virtual to physical address translation, and where the virtual addresses are below. So 30 to 31, 30 and 31 bits is used for index in first level page table. Index in first level page table. 21 to 29. Okay, I guess okay, 32 bits. Okay, 36-bit physical address and 32-bit virtual address. Okay, so I think this is 32. Okay, this is for virtual address. Okay, this is different. I'll draw this one here. So here we have same division, that this will be 12 bits and this will become 24 bits. Okay, so 21 to 29 used for index in second level page table. And 12 to 20, okay, 12 to 20 index for third level to page table, test index of third level page table. And 0 to 12 is offset within the page. Okay, 0 to 12. Now so here in this case, this entire 20 bits will be divided into this part. The first index will be of 0 to 30 and 31 bits. 30 and 31 bits will be for first page level. 29 to 20, 21 to 29, and to 29 this second level. Third level is 12 to 20, the 12 to 20, and finally 0 to 11. Okay, so here in the first level page table, since we have only 2 bits possible, so here there will be only 4 page table entries will be there. 1, 2, 3, and 4. In the second level page table, we'll have how number of entries here in this case is. The number of entries will be the total 2 to the power 9 entries are there. So in each will point to a page table where the number of entries will be 2 to the power 9. Okay, so 0, 1, 2, 3, and 500, 0, 1, 2, and up to 511. In the next level page table, again each will point to another one, which is having again how many entry? 0, 1, 2, 3, up to 51. And now this will point to the actual frame, and here the offset will be calculated from here. This is D is the offset. So P1, P2, P3. This is the situation. The number of bits required for addressing the next level page. The number of bits required for addressing the next level page table or page frame in the page table entry of the first, second, and third level page table respectively. Okay, so the number of bits required for addressing the next level page table. Okay, next level page table. So how many bits, this entry it is talking about in PT, how many bits required in this case? Okay. Now, we know that we have done the paging of page table. Let's say paging of page table. Okay, so page table itself is paged here, and here this is one page, and here though we are having only 4 entry, I required only 2 to the power 2 into 4 byte, and that will become 16 byte of the information. Rest will be unused. Okay, so there will be some internal fragmentation will be there. Okay, so what will be the size of this bit to address this? Now this is going to address a frame, and frame size is how many bits are here in this case is 24. So this entry should be of size, because it is referring to one frame, that this entry should be size of 24 bits. This entry also should be size of 24 bits, and this entry should also be size of 24 bits. Each one will going to address a frame, though we are not going to use it entirely. Okay, but one entity that is fixed here is the next level page frame. Okay, so that entity will remain fixed, and answer for this question is 24, 24 and 24. Okay, 24, 24 and 24. So that at any level it will remain fixed. In a system with 32-bit virtual address and 1 kilobyte page size, only one level page table use of one level page table for virtual to physical address translation is not practical. Okay, not practical. Only one level. Okay, so now 32-bit virtual address, and here in this case is 1 kilobyte page size. So there will be 2 to the power 20 pages will be there, right? And internal fragmentation may be there, but large or not we cannot say. External fragmentation will be not there, but it may be large or maybe it depends, but we cannot say this. The large memory overhead of maintaining the page table. Now here we already seen this calculation, that 2 to the power 20 pages, and a typical entry is of size 4 byte, and that will become 4 megabyte of consecutive memory, and that is an overhead for maintaining the page table. Okay, a large memory overhead for maintaining the page table. Translation process is more or less it is okay, but answer for this question is C, that there is a large memory overhead for maintaining the page table. Okay, so 1 kilobyte of page size, so that will become even smaller, 2 to the power 20. I said sorry, here it will be more larger. Here this is 1 kilobyte, so I require 10 bits here, and here the remaining 2 to the power 22 bits will be here, and that leaves 2 to the power 22 page table entry, even larger. Sorry, wrong calculation. Page table entry. This is another question. Multi-level page table is preferred in comparison to the single level page table for translating virtual address to physical address because it reduces the memory access time to read and write of the location. No, it does not reduce, it increases. Okay, it increases it. It helps to reduce the size of page table needed to implement virtual address space of the process. No, it does not help to reduce the page table size, it remains same. It required by translation look aside buffer. No. And last one is it helped to reduce the number of page faults in the page replacement algorithm. Okay, so it reduces the memory access time to read and write. No, it helps to reduce the size of the page table. Right, sorry, now this is correct actually. Sorry for this. It is I read it did not. It helps to reduce the size of page table needed to implement virtual address space of a process. Okay, now this is a true statement. Okay, this is true. This is false and this is false. Sorry for this. Why the reason here in this case is true? In a single level page table, regardless which process you are running, regardless which process you are running, We need to maintain the entire page table. Okay, we need to maintain entire page table. Okay, entire page table. Whereas here now I have to give a better example, that there is a one page level, one page table, and suppose we are using 4 pages, so that may be possible that here the entries are, this is pointing to another page, and that is giving you the entry to the actual your, let's say, code page, and here is the another entry for the code page, and this may be required. Okay, so understand that let's say this is the pointing to the stack page. Now understand that in one case it has to be contiguous, and I have to maintain all the contiguous entry for one level page table. Okay, one level page table, and here because of the reason of the is offset, offset is contiguous in the nature. Here we have only offset for the first level, then it will go to the next level. I don't need the entire page. Okay, in the next level I may not need the entire pages. All are there, I required, no, I may not need. So maybe I required only 2, but here in page table, because the offset is implemented in this way, I have to maintain the entire page table. In that case, suppose somewhere middle the offset is, because I have to maintain it. Here it can be scattered, like here it can have this and this only. Rest what I can do, no use. So I will not do the swapping, and it will remain in the disk. So per space of a process, that it getting reduced by this. Okay, the next question is this, and it says that a computer system having 46-bit virtual address and 32-bit physical address. Okay, so a system is having 46-bit virtual address space, and it is having 32-bit physical address space, 32 bits physical address space. Okay, and is having 3-level page table organization, 3-level page organization. Okay. Page table base register store the base address of the first level file, which occupy exactly one page, which occupy exactly one page, and second level. Each entry store the base address of the second level page table. Each entry of the second level page table. Each entry store the base address of the here there is some. Okay, each entry of second level. Second level page table store the base address of the third level page table. Each entry stores the PTE, and PTE size is 32 bits. Okay, PTE size is page table entry size. PTE size is 32 bits in size. The computer used 1.5 megabyte 16 4-way set associative virtually indexed and physically tagged cache block size is 64 byte. What is the size of page in kilobyte? Okay, the first question is, what is the size of page in kilobyte? Nothing is mentioned here, so that size of the page we need to find in this case, and in kilobyte. Okay, so for this entry, for finding out this entry, what we need to do is we have to, okay, what is the size of the page table? The formula size of page table is equal to what? 2 to the power number of bits in page number are multiplied by PT, page table entry size. Okay, so that is the size of the page table. Okay. Okay, so now total page table size will be equal to what? Okay, so here in this case, we don't know what is how many pages are there. Okay, so we have to assume here in this case that suppose page size is equal to 2 to the power k byte. Let's assume this entry. Okay, let's assume this situation. Now here in this case, if you talk about this 2 to the power k byte, then number of entries in 2 to the power number of PTE. Okay, correction. Okay, so number of page table entry in a page will be what? 2 to the power k divided by 2 to the power 2, 32 bits, 4 byte. That will become 2 to the power k minus 2. Fine. Now, in the first level, 2 to the power k minus 2 entry will be there. In the second level, 2 to the power k minus 2 entry will be there. In the third level, 2 to the power k minus 2 entries will be there, right? So one level, third level is 2, and it says that your the first level occupies exactly in one page. Okay, so we are assuming that this is also occupied in the same number. The same number of entries are there. That page table, first level page table exactly occupies in one page, and each entry of the store the base address of the second level, each entry of the second level page base address of the third level. Each PT is 32 bit. Okay, so these many entries will be there, right? These many entries will be there, and you will agree with me that this equal to page size, this many entry, and there will be entry for each page. This multiplied by page 2 to the power 4 byte should be equal to what? Should be equal to 2 to the power 46 byte. Okay, now understand here. And why I'm saying this thing? Because there will be, suppose 20 entries are there. So 2 to the power 20 into, let's say, page size is your 4 kilobyte, and that will be equal to your 32 bits. Okay, so that will be always true. Okay, so what it will become? It will become 2 to the power k minus what? It will become k minus 6. Okay, 4k minus 6. Okay, 1, 2, 3, 4k minus 6 is equal to 2 to the byte is equal to 46 bits. Okay, bit byte will be cancelled, byte. Okay, the 4k minus 6 is equal to 46. So 4k will become what? 52. K will become what? 13. Okay, so k will become 13 bits. So here my first question is, what is the size? So 2 to the power k byte is the size, and k will be what? 2 to the power k. 2 to the k is equal to 13. 2 to the power 13, and that will become 8 kilobyte. Okay, so page size here in this case will become 8 kilobyte. Okay, this is the answer for this question. Okay, so we have done the question solving for page table. Few theoretical question is there, and few question related with this page table, and I have solved it. Okay, so that's all for this discussion. Thank you.